Why, hello there. This is Chris Rackauckas, and I'm giving an update on the state of SciML. So I gave a similar / the same talk at JuliaCon, but it was rushed quite a bit to be able to fit into this half-hour period, and so I thought it'd be very good to just kind of take the time to relax and also, be there with the computer, with the internet, to be able to just showcase everything that I'm talking about that's changing with SciML. Now, these slides have not been updated since JuliaCon. It's been about 6 months since then, and so I'm going to be talking about some of the things that have evolved since then, and also just, whatever's new, whatever's on our mind, whatever's changing, because this is always an evolving organization, right? But what I really want to do is I want to kind of lay out the roadmap so that way people who want the extended version of what's going on to kind of have a nice understanding and feel for what's happening in the space of SciML, the numerical solvers, the symbolic solvers, and all the things that's going on in Julia, right? So just get a feel for, again, just so that way we're in the right mind space. What exactly is the SciML open source organization, right? When you're thinking about what the SciML organization is, a lot of people are thinking about one little subset, right? Because a lot of people either think about SciML as it's the differential equation solvers in Julia, or they think about it as it's the tooling for mixing ODEs with machine learning, right? DiffEq flux, SciML sensitivity. Another group of people think about it as, it's the group that makes modeling toolkit. Another group thinks about it as, it's the group that does LinearSolve and NonlinearSolve. Those are just as large projects as well. There's other groups that actually exclusively use it from Python and R. We have a large user base that is in these other languages, right? So there's a lot of different... SciML is a large enough organization that if you ask different people, what is SciML, you'll likely get different answers, right? So if we're going to kind of piece it all together, right? It's a nonprofit organization, right? So it's a group of developers. It's not a for-profit organization. It builds open source software for free. It's part of the NumFocus affiliate libraries, right? So similar to Julia and Jump itself, it is a NumFocus affiliate. And what it really does is it builds and supports development and packages for R, Julia, Python, for scientific simulation and scientific machine learning, right? This includes all of the packages that I mentioned before. And what that really means is that it's over 100 GitHub repositories. I think we've hit about 125 now. With that, about many of those are tens of packages themselves, right? So what do I mean by that? This is something I'll highlight a little bit later as well. If I go into here and I check out ordinary DiffEq, you click on lib, each of these is a different Julia package itself, right? And so even when we say we have, 100 GitHub repositories, we're really talking about, about it's over 200 Julia packages. I think it was like 210 last time I counted. Right now, all of them are MIT open source licensed, though, there's different questions about different licensing to be happening for various different reasons, and that's a whole discussion to be had itself. There's over 20,000 GitHub stars across a set of packages, so 22,000, I think, is a marker that we hit a few months ago. About 100 unique contributors monthly. This means about, one unique person per package. Now, it doesn't really line up like that because you have a lot more contributors to something like the differential equation solvers and modeling toolkit than we do to other libraries. But I mean, you can almost think about it as, about 100 people uniquely each month, where about 20 of them are core maintainers owning some source of the project. What I mean by that is, there's about 20 people who you can reliably show up every single week, or, say once a month in a way that is, in a package that is moving less often. And then there's another 80 each month, which might just be doing a drive-by, one commit here, that are not necessarily longer-term maintainers, right? And that group of the 80 is rotating out all the time, whereas the core 20 kind of stick around. And this also means that we also have about 5 to 10 students and other trainees per year. Many are associated with the MIT Julia lab, right? This is the lab that I run with Alan Edelman in MIT and CSAIL. where we have, these undergrads, master students, and PhD students whose research is focused on topics such as high-performance computing and scientific machine learning, and all of them tend to have some role or some usage or some development of the open source libraries, right? Many of the companies that have spun off, including Julia Hub, NeuroBlocks, and Pumas AI, house a good number of these maintainers as well. In fact, I recently gave a talk about that on the Open Teams YouTube account. Let me see if I can find that video really quickly. So if you go to youtube.com and then you go check out Open Teams, right? If you go check out Open Teams, you'll find that there is this video there that is building in a product in the open.
Welcome.
Rackauckas,
I'm Inessa Pawson.
That is me, the one, the only. So this video right here, if you look for this community event video, you'll find that it talks about Julia Sim.
Open source
and
program.
what this is really all about is it's talking about, who is involved in the open source development and how do the different entities such as the MIT Julia Lab, how who is actually coming from the Julia Lab, what are the projects that they've been working on, but also then we talk about, who are the maintainers that come from things like Pumas AI and Julia Hub, right? And it really kind of tells a story about the maintenance of this open source libraries and how a lot of the maintenance is happening through these different entities, right? So I'd say maybe about half of the maintainers come from one of these entities that I'm associated with, and then the other half of these maintainers are just from the wider world of people interested in open source software. So what we do is we probably have about 10 grant submissions per year, trying to, that could be anywhere from 10 to 30 in a given year, related to try to get more folks into the SciML organization, usually through MIT or one of these affiliated parties or non-affiliated parties or the probably the most common one ends up being, we do a lot of partnership grants. So, for example, someone in climate science might be looking to build a better climate model, and they want to do, scientific machine learning and climate. And so we're collaborators on that grant where, our 50% is doing a lot of methods development, and those methods are all going to the open source software, right? So that's how a lot of MIT grants work. A lot of Julia Hub grants are similar, where it's in partnering with the national labs or other groups such as, the Army or Navy, or, develop cardiac models, but then half the working the cardiac model is better differential equation solvers and automatic differentiation tools, right? So there's this kind of large ecosystem that's been built up. In fact, most of the open source organizations in NumFocus tend to have about 20, 30 maintainers or 20, 30 contributors that they're talking about, right? So in some sense, SciML and the Julia programming language itself, the two of them are kind of the two largest organizations in NumFocus, if not the largest, then at least quite up there as some of the largest, right? These numbers of people contributing actually outpace a lot of things that about, like NumPy or SciPy, because I would attribute that to the success of the Julia programming language and getting people who are users to be able to turn into contributors, right? Where in a lot of other languages you have the core libraries and written in C or Fortran, like SciPy is written in C and Fortran. All of its users are in Python, and so you don't tend to have as many people translate over. In the SciML organization, we've had a very good number of people translate over from users to developers, and so the ratio between user to developers is like one developer per 10,000 users or something, right? Or one developer for 1,000 users, which might sound like a lot, but for a lot of open source organizations, it's like, one developer for 100,000 users. So we've done really well at translating users into developers through these different programs, and also just through the sheer, simplicity of changing, because it's all one language, right? And I, Chris Rackauckas, am the BDFL, which means I'm the one that's been stupid enough to sign up for trying to maintain all these libraries and give it a unifying force. Right. I would say that these days, my main goal, of course, I'm contributing a lot of code, and in many cases, the majority of the code for majority of the libraries. But, there's a lot of projects that have other majority code contributors right now, like Ordinary DiffyQ and Modeling Toolkit. Ordinary DiffyQ, probably Oscar's putting in more code on average each month for the last few months. Modeling Toolkit has Ayush, Symbolics has Ayush. We have other things like, DiffyQ Dev Tools. I think Henrik Menchoa has been, so there's a lot of large pieces within the organization that have had more people who are the majority contributors, at least within the last few years. That's been a very nice development. But I think my role, having been there from the start and being a maintainer of all the different libraries, is really to try to make sure that the organization keeps this unifying force and keeps this unifying API, and always asks this question about how do we make sure that different packages talk to each other well, and how do we have algorithms that are able to run the span through the whole ecosystem in a way that then gives you a better improvement of all the parts together, right? And I'll be talking about some of the cases with that. And so again, these are the same slides from JuliaCon, and so at JuliaCon I had to keep this to 30 minutes. Good thing here I do not have to, so I'm already at 11 minutes, and this is exactly the issue that I would run into. So let me try to, again, I'm going to be summarizing, but this should be like the big, version of the summary, not the little version of the summary. This is the grand poppy of summaries. Yeah. So, if you haven't already, everything that you can do to help out the organization. Again, before I get into the meat of it, anything that you can do to help the organization is always great. That means joining our chat rooms on the Julia Lang Slack, right? If you haven't been to the Slack, this is where a lot of the user and developer talk discussion happens. So I recommend going there, even if you just have questions for quick bug reports. More follows on Twitter is always helpful, though these days, Blue Sky, Fostodon, and all these other things. Also, if you want to get, so any updates, if you want to get immediate notices about them, that's where you'll be able to get them. LinkedIn as well. Give us a follow on LinkedIn. There's also a LinkedIn community for SciML in general. Let me show you how to find that. Right. So there is this SciML group on LinkedIn. This is a company page that was made for the nonprofit, and we post a lot of videos as they come out for different things that are built on the SciML organization, different things about what's being used and how things are being used and what's next in the community, and also to kind of share different funding opportunities if you're interested in that as well. But last but not least, star the libraries, right? If there's anything that you can do that's the most helpful, you just go to one of the libraries, you click the starred button. Being able to just have these metrics that just say people care about this is one of the ways that we can then go to funding agencies and say, hey, look, we have the metrics that show that, here's how many users we have. They really care about this. This is changing their science. Can we use this to be able to fund, students so that way they can, actually have a house while they contribute to open source, right? Because again, open source software is free, and so we need to have some source of funding in order to make sure that people have a house if they want to work on it, right? And so most of the funds actually go to student projects, right? In fact, most of what we do is student projects and other developer projects that tend to be student focused as well. Right. Let me just show this. If you go to community, you go to developer programs. You have the SciML, this Google Summer of Code, which we run every year. In fact, right now we're in the Google Summer of Code season. Students are finding projects in improving things like ODE solvers and other aspects of partial differential equations and symbolic tools, right? Students will sign up for this, and they're paid for the summer to give contributions. We try to actually extend that program beyond what Google will fund. That's what the SciML Summer Fellowship is for, and a lot of the donations community actually go through the SciML Summer Fellowship. That's probably one of the leading payouts that we have. Also in other smaller objects like a season of docs for improving documentation. NumFocus gives us some money for funding a student. That student, for example, has been working a lot on. There was one that did documentation, and another that been working on the boundary value problem solvers and the optimal control ecosystem, which we'll showcase at the next JuliaCon. But then the other large project that we use some of the funding for is the SciML Small Grants Program. A lot of this has been actually my own personal personal donations so far. So if you have any topic that you want to add to this, if you give the donation the money, you can also say, here's a topic that I want, better documentation for modeling toolkit, better, improving the type stability testing across some library. You can come up with anything you want with it. Right now, I kind of wanted to pre-start the program just by using some of the existing funds from a previous grant that we had, also some of my own personal donations, and so some of the projects are making neural PDE more maintainable. This is a big thing where we want to do more work on physics of formed neural networks, and to do that, we need to kind of do some updates to it, so that way it becomes an easier project to get new students engaged in. So it's kind of this big hurdle we need to cross, and then it becomes more self-sustaining. So there's these projects also with SciML operators, bumping our benchmarks, yada yada yada, right? So there's all these different projects that we've highlighted. Most of these projects get picked up by students around the world who then sign up for it. They show that they can solve the problem, and that ends up being their catalyst to then do more, right? So if there's any project that you in particular are interested in, this is a list that can continually change, and we're happy to take donations for anything that in the space of SciML and in the space of SciML and symbolics and the whole space, right? Even Julia more broadly, because there's a lot of things within, say, improving the type stability of distributions.jl. We'd be happy to, have someone be, as long as we can get the right reviewer to that, if it's not within our organization, we need to make sure that we have the right people who can review and merge the code, right? That would say yes, they would read this person's code, but as long as it's in the space, we can figure something out. So that's a long tangent again, because I get to have long tangents in this format. But start the SciML repositories, go and click the donation button, and all those together are different ways to be able to have us help us run some of these developer programs, which effectively just helps us improve the number of people that we can get involved, right? Because only so many people can do this purely for free, and being able to get more students involved is really a helpful thing in the long run. I mean, a lot of these students end up going to either the Julia Lab, or a lot of them end up becoming interns at some of these companies. Like, this is how we get people into the ecosystem, how we find better people, and how we keep better people. So, the simplest thing of just giving a star, it just helps with grant opportunities. So just please, whenever you can. So what exactly is the SciML organization? If we're to try to put it in some, refined form, I would say, let's go to the documentation. If you look at what we do, right, we build tools for modeling, we build solvers, we build analysis tools, machine learning developer tools, and also we help people use this within real applications, right? So one of the core pieces that you might see is the solvers, right? That's probably the headstone, or that's death. It's probably like the focal point of the organization, right? Things like linear solve, nonlinear solve, differential equations, integrals, optimization, and jump processes.jl, right? These are these kind of big, projects where most people would say, like, since the 1970s, you had a single version of these things created, and you've never had people, spend significant amount of time rebuilding these things from scratch, right? Most of the ODE solvers that people use are the ones from 1990, like the good old, LSODE, CVODE, etc., that are now just state alive, right? We're the idiots that have decided that let's start to rewrite a lot of this stuff from scratch, because in the last 30 years, there have been major advancements in numerical analysis and numerical algorithms, and we can only make use of all these improvements if we actually have solvers that build these from scratch, and then we go beyond that, right? So a lot of the work in the organization early on was a reconstruction of these old solvers to be able to show that we can get bit for bit the same results, right? In fact, even with differential equations, we have implementations of, say, Dupree 5 with the given options that give you exactly the same solution as the Fortran code, right? But of course, we learned a lot from that. In fact, we found a lot of bugs in the old Fortran code that everyone says is, the gold standard. And so after fixing these bugs, doing performance improvements, there's still some options you can set to make it so that way it's bit for bit compatible. But a lot of our outcomes have now gone beyond. And so that's what we've done first in the case of differential equations, but then we really branched out to optimization libraries and nonlinear solvers and linear solvers and this whole space of solvers, right? The other thing that we've done is that we've also made this work with automatic differentiation, both forward and reverse. So solving inverse problems and parameter estimation problems, such as with diffie-param-estim, diffie-Bayes, and also just letting it work with general optimization libraries has been a strong focus of the organization. So then that also means this connection with machine learning, the scientific machine learning, is really making sure that all of these solver libraries are compatible with all the machine learning libraries. Then we have a lot of tools that are kind of growing for specifically handling partial differential equations, method of lines for, method of lines discretizations and finite difference and finite volume. You have neural PDE, which is the physics-informed neural network form. We have neural operators. There's connections to finite element tools and all sorts of different tooling there. So that's even just looking at the solvers portion, and you can see even from the summer that we've actually changed some of the documentation around here, where there's newer advanced solver APIs like solvers that are specific to GPU environments and other static environments, highlights more of the boundary value problem stuff and the growing optimal control ecosystem. But even then, that's only one aspect, right? We have all these modeling languages. So these languages allow you to symbolically build up models that then generate code for the solvers. Model libraries and importers, so pre-built models, importers, so that way you can read from Modelico files, or you can read from SciML Toolkit and SBML files, so importers from other languages. All the symbolic tools so you can manipulate models at a core level, but then also array libraries for representing the computations in structured forms. Now, you even get to some of the analysis libraries where you can do things like parametric analyses and uncertainty quantification, machine learning libraries for things like building surrogates on simulators, implicit layer deep learning like neural ODEs and universal differential equations, symbolic learning for taking the learned differential equations and turning them into symbolic representations from the neural networks, and also a lot of automatic differentiation tools. And then we have the wide array of developer tools, which, these are things that a lot of people might not be interfacing with as directly, but these are all tooling for a lot of tool developers, including things like, better tools for computing matrix exponentials, tools for representing noise processes, which is used within the stochastic differential equation solvers, tools for improving automatic differentiation performance, tools for building interpolations, which actually this is a bit more a user-facing numerical utility, quasi-Monte Carlo sampling libraries, things that just make finding first on functions faster, which is used to make the interpolations faster. There's a lot of interfaces, so that way we can, every time that we want to be able to say, hey, look, the way that you work with this problem, ODEs is the same as PDEs, etc. These are all have these well-defined interfaces for the SciML problem and solve types, interfaces for automatic differentiation, interfaces for how parameters are defined, interfaces for indexing, and yada yada yada. And then finally, we have things like our style guides and community practice guides, and all these little things, along with little tutorials and such. So if you've never seen these, I highly recommend it. If you're trying to get interested in open source software, we have all the guides for how do you contribute to the libraries, all written out with what the standard practices are. And then we also have a style guide on everything that you should do in order to, write code in a way that is following the SciML style, which we use within our libraries, but also we recommend that users use this as well because it tends to be a fairly nice and robust way for just writing general Julia code. So that's the organization. Again, there's, a lot of people may focus on just one part, just use the nonlinear solvers or just use the ODE solvers, but that's the organization as a whole. And so if you try to map it out, kind of say like, okay, what is SciML? There's the modeling tools written in British English, because this chart was made in part by Torkel, one of our main maintainers of Catalyst. So sorry for the British English in here. But yeah, so we have the modeling libraries, right? Modeling toolkit and symbolics, which are used to be able to develop the other modeling libraries on top, like Catalyst, orbital trajectories, right? I mean, there's a whole long tail of these modeling libraries, which are not in the SciML organization, but are built on top of SciML tools and maintained as with the general target being modeling toolkit. We have the equation solvers. We have tools for simulation. This is where we're saying like, okay, tools for solving math problems, integrals, nonlinear solves, linear solves. But then you have simulation tools like solving ordinary differential equations, stochastic differential equations, partial differential equations, and the whole lot. Tools for solving inverse problems, which some of them are direct interfaces, like how do you just get the derivative when you need it. Tools for simplifying the interface to optimization, and also just directly allowing people to use optimization tooling, which then has wrappers to optimization libraries. There's also a lot of the automatic differentiation tooling, which more and more has been split out of SciML, which is a good thing because again, that means that there's more maintainers, more distributed work on this. In fact, I really like to highlight a lot of the work of Guilherme and Adrian in the last few years on differentiation interface, right? A lot of what was differentiation interface was really kind of internal to SciML and just internal to the ODE solvers for many, many years. We abstracted that at first to abstract DifferentialEquations.jl, and then they really took up the reins to be able to improve that. So they've improved upon abstract DifferentialEquations.jl. They've improved upon sparse differentiation or sparse diff tools.jl. They've improved upon some of the tooling that is like the internals of SciML sensitivity, the internals of optimization.jl, and over the last year we've actually had a lot of movement where optimization.jl, ordinary diffeq.jl, and some of these libraries are now using differentiation interface rather than having their own kind of versions of this. So yeah, big shout out to those two. We've done a lot of really nice work to, take what we had as this kind of, internals and kind of make it so that way it's usable to other libraries as well. I mean, for most ML users, you won't really notice a difference. We were using AD types and, it's the same type interface, the same. It's really under the hood. We no longer have our own versions in a lot of the libraries. We now have a standard version that matches the performance and matches the feature functionality that we had before. And so now it's much easier for someone to be able to say, build a new solver that uses the same internals. So automatic differentiation is kind of all outside at this point, and even during the last 6 months, it has been increasingly on the outside, which is great. I mean, now again, SciML people tend to still be maintainers of a lot of these libraries. Like finite diff is almost exclusively maintained by SciML people, though this is changing more and more, and that is of course better because that means that more people are just picking up maintenance, which means more maintenance to go around, and that's happy for everyone. So and there's also other, of course, non-SciML packages like plots that SciML folks are major contributors to, or people that we work with a lot, DynamicalSystems.jl, bifurcation.jl, which aren't necessarily in SciML, but we talk with the developers probably every single day, and they use a lot of our tools, and we recommend people to use those libraries. And so there's, for example, there's no reason for us to build bifurcation tools because bifurcation kit is great, and a lot of the analysis tooling, for finding chaotic retractors and such, go use different DynamicalSystems.jl for that. That is the preferred and the preferred partner of SciML, if you want to give it a marketing term. So that's the organization at a glance. And if this was the JuliaCon talk, I would have had to stop right now to just define the organization before I ever get to the roadmap. So there you go. So okay, let me kind of describe the SciML organization as a whole. And for each of these, I put a maturity level. I think there's a different slide that I actually define the maturity levels. So as an organization, at an organizational level, the organization is pretty well matured, right? And what I mean by that is it has, commercial entities, it has, the nonprofit entity, it has the academic entity, it has some secured funding resources. It's been around for about 10 years, and these funding resources have only seemed to grow, right? Of course, there are always going to be some uncertainty, especially with the different political events going on throughout the world in places like the U.S. That can change funding on a dime. But the SciML organization has, a lot of redundancies around to make sure that it can stay afloat in different environments, right? So that's what we mean by maturity level high here. It doesn't mean that every single package is mature at a maturity level high, right? As we'll point out. But what it does mean is that as an organization, we have, bylaws, we have contracts that we know how to easily give people money for these granting opportunities. So it's not like if we wanted to give a bounty to a new project, or if someone said, hey, can here's $500, can you make it so that way the modeling toolkit documentation is better? We have a system where we just put something on the website and it's the contract's already worked out, the way to pay the funding's already worked out, all this stuff, or we already have the admins, the organization exists, it's been stable, and the system is there, right? But so let me kind of describe how we got to this, to kind of give a feel for it. The first versions of the differential equation solvers, which kind of were the catalyst for the SciML organization in the first place, they were actually written as MATLAB plus C code to target Xeon Phi accelerators. It was actually for a stochastic differential equation paper for new adaptive methods in stochastic differential equations. Funny story. Actually, the reviewers came back, and of course, reviewer number 2 asked, how can you prove that this code is sufficiently fast? Because it was kind of weird to kind of ask, how do you know that this code is sufficiently efficient, to be able to say that it's an efficient code like that in quotes, right? Because there really wasn't a adaptive SDE solver they could just pick up and test against, right? So how do I know that this adaptive method is good? Well, what we can do is we can create SD solvers, but let's create OD solvers in the same exact way that we built the SD solvers, and then let's test the OD solvers against the C and Fortran codes. And so that becomes the first version of the Julia codes, because we said, okay, let's create the SD solvers in Julia so we can make the OD solvers in Julia. And it makes it very easy to test against the C codes, because there's a nice sundials wrappers and nice Fortran wrappers, and turned out that we were able to outperform the Fortran and C codes. And so, what we were just writing SD solvers, we finished the paper, but by the end of that, people just kept on asking for more things on the OD solvers, and boom, that became Julia DiffEq, right? The differential equation solvers really then kind of started their open source journey back in 2016, which is almost a decade ago at this point. We ran a workshop at JuliaCon Berkeley where we kind of showed the start of a lot of the parts of the organization, right? So many of the modeling tools like DifferentialEquations Biological, which is now rebranded to Catalyst, parameterized functions.jl, which is now rebranded into Modeling Toolkit. A lot of these came into existence. The differential equation solvers were there. We ran workshops on these same tools, right? Of course, back then, they weren't as fast. They relied a bit more on the C and Fortran code. There was a lot of things that we didn't handle in terms of larger scale problems and yada yada yada. But that was where everything kind of started. Especially along those lines. That was actually the kind of the genesis of Pumas. That was the first time I met with VJ, and of course Pumas then became something that was a commercial entity now. Well, it was turned into a commercial entity in 2019, and that was one of the early funding sources for the organization, because that field of pharmacometrics makes big use of all these different solvers, and so they were kind of developed in hand, co and co with this kind of use case. In 2017 or so, many of the analysis tools had started, right? So in 2016, we started with a lot of the solvers and some of the modeling libraries. Of course, the first thing that people started asking for are things like global sensitivity analysis, expectation, uncertainty quantification, and all that. And so and also a lot of things to do with parameter estimation, right? And that's when we kind of started this journey of saying, okay, what do we do? What is automatic differentiation? What are adjoint methods? What can we do about global sensitivity analysis? And so 2017, a lot of those libraries really started to be created. That became its own kind of study in a sense. And then in 2018, I think that was actually when I moved from being a graduate student to having a position in MIT mathematics in the mathematics department as applied math instructor. And that you can kind of think about it as a catalyst for the SciML organization as a whole, because then I was moving from this position of being a student myself to now a position where I can apply for my own grants, or where Pumas AI then became an actual company. Became affiliated with Julia Hub, and so it was no longer me with some students I was mentoring, but now it was something where I was starting to get grant funding. We had these company opportunities, and started to be about the growth of the organization and really establishing funding resources and the growth of other maintainers. That also happened to be coincided with when a lot of the work on universal differential equations and differentiable programming happened, right? Because, I go to MIT and people say, hey, the hot new thing has to be AI, so why aren't you working on machine learning? And I go, I like differential equations. And so how do you stick differential equations and machine learning together? Well, that becomes the genesis for SciML, right? And a lot of the SciML methods and automatic differentiation methods, so still keeping the same vibe as the original goal, all this stuff with the differential equation solvers and high performance, but now really kind of with this extra bit of machine learning added to this whole ecosystem. Whereas finally in 2020 we renamed to SciML, because before it was just Julia DiffEq, but at this point we had 10 libraries for differential equations and 90 libraries that were not about differential equations. So we rebranded around scientific machine learning, and the idea of building an entire solver ecosystem and modeling ecosystem that is fully connected with the tools for machine learning. And this is when the SciML book was created for the new graduate course at MIT, and it's kind of was in the training ground for a lot of the maintainers that would come afterwards. A lot of non-differential equation packages that we were waiting on, for example, LinearSolve and NonlinearSolve, they started this year because we said, why are we building specialized linear solvers in the differential equation solver? Well, we were too scared to take on other libraries. Well, SciML is about not just differential equations. We're not Julia DiffEq anymore. We're SciML. We're going to build other libraries as well. So let's actually make integrals.jl. Let's make optimization.jl. Let's make these good libraries, right? They're not just subparts of the differential equation solver. They're their own libraries in their own respect. And so that all really started in 2020 when we kind of changed the name to kind of say, here's our expanded scope. And another big change too was that development practices became a lot more precise, as many contributors and maintainers had worked with or continued to work with Pumas AI on things related to regulatory compliance, right? The big thing in 2020, of course, was COVID, where Pumas, which is again this software built in Julia, was the main catalyst behind making one of the quickest clinical trials ever for the Moderna vaccine, and then finally the pediatric vaccine for Moderna, right? This, of course, is public knowledge, so you can find the previous JuliaCon talks by the director head of pharmacometrics at Moderna, who described this, right? And so that 2020 kind of ends up being this turning point for the organization, where it now is embedded within this whole industry of pharma, and it's no longer just about ODE solvers. It's something that's about all the space of scientific machine learning, and it becomes established as something that has this graduate course at MIT. Like, these are all major steps beyond just, hey, look, we're just some people hacking on code. Now it's an organization that kind of has uses and influence in all these different domains. 2021, I leave the academic route to become VP of Modeling and Simulation at Julia Hub. This starts the Julia Sim project, where the Julia Sim project is, it's a commercial project to develop a modeling and simulation engine, which has a graphical user interface, yada, yada, yada. That's a whole different talk. But one of the big things here is that since it's, if you think about, like, say, the Modelica space or the space of graphical modeling tools, it's made to develop the next generation that is scientific machine learning influenced, but built on these Julia SciML tools. And so this has actually been the largest set of hiring for people who are maintainers of this organization. I think that the developer team's around 25 folks or so at this point. And you can go to this talk on the open teams or organizations YouTube to kind of see what Julia Hub has kind of done for the SciML organization and a lot of the folks involved in different open source libraries, right? But that ends up being this kind of one of the main things that this ends up doing is it really kind of is the catalyst to make Modeling Toolkit a direct competitor to these things that you have in Modelica, like the Dimula. And so that really builds out Modeling Toolkit and the symbolics library, so that it becomes a whole computer algebra system with a whole acausal modeling tool. And this also led to some of the early funding that would be used for integration of enzyme throughout the organization, right? So that is kind of one of the other major step changes in terms of the size of the organization. Next, then we had the organization that was reworked to enforce static compatibility and reduce first time to solve, right? One of the big things that started to happen once we had the Julie Sim project was we needed to start targeting embedded devices, so the ability to build small binaries, be able to have, startup times reduced, be able to have low latency in GUIs. This became a really big push that could be then reproduced throughout the whole organization. And so, but that also led to a lot of this kind of, professionalization, a lot of the organization. So documentation, error messages were reworked. Everything went from having just a single documentation to having these, doc strings from which the documentation is built from. Every function needs a doc string kind of style. We wrote style guides. These global CI practices were started. And importantly, a new deep learning library came out of the MIT Julia Lab, which Lux.jl, which was much more focused on the scientific machine learning interfaces. And then kind of, from 2019 to 2022 or so, we're kind of in this weird, Flux is a good machine learning library to extend and such, but doesn't really do things right for the way that we need to do things for scientific machine learning. Whereas so we really then kind of started to take that in-house and take charge of that in 2022 with Lux.jl. And also this is when a lot of the interface libraries really became integrated, right? Instead of just saying we have these interfaces, this is how they're defined, all these interface definitions started to become their own libraries, so that way they become tested and become documented interfaces throughout the organization, right? So again, the 2022 is that start of that phase of a lot of the professionalization of a lot of the modularization and all that. And finally in 2023, we get the SciML global documentation released, right? This documentation of having one documentation of it all together, this was actually only in 2023, right? And I think this kind of cemented SciML as this is organization over all of these different domains, and really kind of helped piece together all, the whole story, along with most of the other solver packages like linear solve, nonlinear solve, integrals. They led to a level of completeness, right? I mean, again, remember a lot of those libraries were kicked off in 2020 during the renaming, right? So early in 2021, you go to NonlinearSolve.jl and you're like, this library isn't as great as differential equations. Yeah, well, differential equations had half a decade to get there. Nonlinear solve was in its first year. But by 2023, we started to say linear solve, nonlinear solve, integrals.jl. These are libraries that are now usable, and they're hitting the level of maturity that's similar to the differential equation solver, along with the PDE tooling. And then a lot of the tooling that was built to target Flux is now set up to target this new library Lux, right? And so you can kind of see how, it started from differential equations, and then, things got kind of, stabilized around 2019, and go, what are we going to do next? It's kind of a crazy decision to then say, now that things are starting to work well, now that things are starting to be stabilized, let's take our domain, which is this size, and let's make our domain this size by saying we don't just do differential equations, we do differential equations plus every other numerical solver and the machine learning integrations with it. So it was a huge scope growth, right? But with the scope growth, we then we're established larger organizations to get more maintainers in, and then over the next few years, we're able to kind of fill in that space of the scope that we set out for ourselves. And then I think one of the major changes that are more recent is the SciML small grants program, right? To start saying how can we grow the number of contributors that we have, right? That's where this small grants program started in 2020, along with other major improvements in terms of enzyme integration and GPU solvers. And again, one major piece within 2024 is the rollout of tooling for anti-allocation and dynamism checking, right? So things like, if you haven't checked it out before, allocheck.jl, right? allocheck.jl is a library that checks whether a function is allocating. This is a project that was kicked off in the Julia Sim team to be able to have the right tooling in the compiler to be able to test for whether code's allocating, because we need to run these codes on embedded real-time controllers. And so what we need to do is we need to make sure the whole SciML organization is compatible with outputting code that has this property, right? And so that all kind of came in 2024 with these extra tooling, and now we're trying to roll out this tooling to be used in the testing throughout the organization, right? And then in this 2025 frame, we've been working a lot more on symbolic numeric PDE tooling and integrating better with a lot of these PDE tools. So a lot of symbolic numeric improvements, which I think that'll be my next JuliaCon talk. So I'll leave it for that. But the other thing to kind of look at is let me figure out where I find it. The other thing to really look at as well is that now we got all of this tooling for static handling. One of the other big advancements is the ability to build binaries, right? This was something that was kind of kicked off because of needs in the at Julia Hub for the Julia Sim project, and so we now have the ability to create binaries directly from Julia. And we're demonstrating this on controls type of applications. And of course, a lot of the things that are being done here is to make it so that way tools in SciML, like modeling toolkit and the differential equation solvers, can be used to generate small binaries that can be used in such embedded environments, right? And that's really big target for the 2025 timeframe. So that's just the organization. So hopefully that gets you a good feel for how we've grown. Again, we kind of went from a solo project to just some hackers on some open source libraries, to then things that had MIT involved, Humus AI involved, Julia Hub involved, and all these other organizations that are now kind of intertwined with the SciML organization. And of course, you still have some other random hackers all over the place. Open source is for the world, but this kind of also gives it a grounding, so that way there are entities that are reliant on the software, and there's entities reliant on the software being used in regulatory reasons, and so there's a lot of tooling and stability that have been built up in order to accommodate the regulatory concerns of a lot of these use cases. So when we're talking about the maturity level, here are the different definitions that I'll use, because now we're going to go through different parts of the organization. So the thing to kind of highlight here is that the SciML organization it's about 10 years old now, but that doesn't mean that everything in the organization is 10 years old, right? A lot of the ODE solvers were here from the start. Though, of course, there's even newer ODE solvers in DiffyGPU that came much later. But, then there's other libraries like LinearSolve, NonlinearSolve, integrals that only started when we did the rename, right? And so, there's differing maturity levels throughout the organization. That's to be expected, right? And so one of the things that we need to do when talking about the state of SciML is we need to really highlight the differences between them, right? Because, some of the ODE solvers are like, they're used in regulatory medical cases, and then some of the other solvers are a student's project from 3 months ago, right? They're not all the same. And so when we're talking about the different aspects of this, we need to establish some maturity levels and some definition of that. And so what I want to refer to as high is that, this is something that is battle hardened. The interfaces are well defined. It preemptively throws high level user legible error messages. So it doesn't rely on the auto generated error messages when you hit a method doesn't exist. Fully documented, has an expansive test suite, ensures that edge cases are handled, has tutorials, workshops, and other training materials, right? That's what we call a high maturity library, something that has had all the edges rounded out. A medium maturity library is one that has recently reached maturity, which means it probably has a full set of features. But, and when we say, has a full set of features, then we always mean that the documentation, the benchmarking is there to show that it's, fast and robust. and that, it's tested highly against classical implementation, so that way it's correct, and we show that it's, also performs better in some domains, yada, yada, yada. But, normally when you hit that level, because you have all the features, because you have all the solver pieces that are working really nicely, doesn't mean that library already has good error messages, good documentation, good tutorials and workshops and whatnot. So we call that just medium level maturity, right? Then the code works. The code works really well, but it's not like your average undergrad could just go to the documentation and pick it up as at that level, right? Low means that these libraries are still in heavy development. Means that, there's major version updates, so major breaking updates that are planned for the near future, and we kind of have a goal of what we want the library to look like, and it doesn't look like that yet. Maybe maybe the methods are matching the performance of the classic C or Fortran codes, and so we're like, oh, we need to do this, this, and this to make it better, so we're going to have a future version that changes this, or it might not even be there yet, so we're still recommending, calling some of the wrapped Fortran codes as the main solvers, right? It's one or one of the biggest things also is just that we might have testing for flow 64 and flow 32, but not every automatic differentiation library, not every combination with every array library. It's not as battle tested. And then we also have the research level, right? These libraries are effectively unreleased. A lot of them are in the stage where they might have even had their first version to the general repository, but they don't even really have a major documentation up yet or anything. They're open for early adopters because we do a lot of our research in the open, right? So people can start testing it out and start to see like, okay, I have this problem where no other optimizer can solve it. Let me try to use this new optimizer. But we don't really make a claim that, oh yeah, it's going to work with every automatic differentiation library. We don't even know if it's that great yet, right? It's still in the research phase, but we feel no reason to hide code. We do all science in the open, and so you can see all these algorithms in their development process, and kind of and this was really helpful for us as well because someone will come use this library and say, hey, look, it's really good for modeling electrical circuits, and someone else will say it's really bad in chemical reactions. Great, that helps us write the paper. So there's a lot of this research that happens in the open. Of course, these are the fringe libraries. These are the solvers that are the 200th one on the page. And they're usually highlighted as, kind of in this earlier stage. And so, that kind of shows like all these can be within the same organization. In fact, for different ODE solvers, you have some in the research phase and some that are in the highly robust phase, right? You can't, within a repository, you can have a lot of these differences, but in general, we can kind of think about them at a repository by repository level. So, okay, with that being our criteria to start talking about and our basis to start talking about all this, let's talk about the numerical solvers, right? The numerical solvers are this kind of area over here where we have nonlinear solve, linear solve, integrals, ODE solvers, and PDE solvers in that whole part, right? An incomplete list of the SciML common interface is that, you have linear solve, which you have a linear operator defined by a parameter, and then you can differentiate, AX equals B, which is just A / B, but of course there's many different algorithms there. You have NonlinearSolve.jl, which is root finding, find where f equals 0. You have differential equations, you have integrals, and you have optimization solvers, right? These are your standard sets of mathematical problems that you tend to run into. And of course, the list is growing and growing, and we'll talk about how that's growing. But this is kind of like the core of that common interface. Of course, the first library to talk about is DifferentialEquations.jl with a maturity level that is high. Because again, DifferentialEquations.jl was the first part of the entire organization, right? Again, it started from a basis in 2015 or so, where there was these MATLAB codes and C codes written for Xeon Phi accelerators, which is this first version of these high-performance ODE and SDE solvers, and then it was kind of converted into Julia in order to show that we could improve, to show reviewer 2 what's up, but more correctly, to show that we could make these OD solvers and SD solvers in a way that's efficient and in a way that is, affecting a new community. And then, they ended up over time getting event handling, type genericity, high performance, and of course, a lot of adaptive SD solvers were one of the early parts of this development, right? So that was the genesis of the organization. But we quickly found that the space of differential equation solvers can be way too large for just a single package. You start to get a lot of load time issues if you start to add in hundreds and hundreds of solvers just in one library. We realized that the differential equation solver libraries were way too large in terms of, trying to stick every single solver in there. And so the best thing to do would be to split it up into different libraries on domain. So we had, stochastic diffeq, delayed diffeq, sundials.jl, targeting different spaces with different solvers with these common interfaces. One of the main One of the big improvements then at this time was we were able to then see that the core Julia solvers tended to actually be the best performing methods for non-stiff ODEs, because they're based off of new techniques like the SIT solvers and the Vern solvers with PI adaptivity. So it really kind of kicked off this new wave of differential equation solvers built off of the new tableaus and such that have been developed since the last time any of this development happened. And also, we had that a lot of these specialized Rosenbrock methods achieve top performance on small stiff problems, right? So there was still a large domain of differential equations, which we weren't the fastest at, and that would be the case of the large stiff equations, especially with partial differential equations. But a lot of the tooling for that was easily available through sundials.jl, and so even without having those as the native solvers in Julia, the Julia ecosystem still at least became the best for using these types of methods. And then the next we had a lot of the work was to say, okay, let's make sure that the larger stiff equations can also hit that same level. And with that, we had a lot of the work on the S-strict methods, the IMEX methods, Raddau exponential integrators, and also the auto switch methods were added around this time in 2018. And then in 2019, we had a lot of the automatic sparsity support come, and that really made it so that way large-scale PDEs were really the case. And this is really started to have this switch where, if you have large enough partial differential equations and large stiff equations, one of the solvers in the Julia ecosystem tended to be the best. We had the QNDF solvers and the FBDF solvers that really rival sundials in most cases. We never really created something to the IDA case, so that's a different discussion to be had. But yeah, but at that point we had a lot of the solvers for small stiff equations, large stiff equations, small non-stiff equations, large non-stiff equations. Where if you go to the benchmarks, you then be able to see that there was some Julia algorithm that was the fastest in each of these domains. And then also there's the long tail of symplectic integrators, IMEX integrators, etc., where it's kind of hard to find other cases of implementations of them. And that kind of happened in this 2019 to 2020 range. And then we started to say, okay, what's the next thing that we have to do in terms of the ODE solvers? Well, just more performance, but also more generalization. So, one of the biggest things that then happened to these solvers, and the largest breaking release in a long time, was the change to NonlinearSolve.jl, where we said, okay, we had NonlinearSolve.jl integrated into the solver itself, but now we had this change to SciML. Like, why are we building this? Why not just give everyone this ability to handle KLU versus UMFPAC and all these different ways of choosing linear solvers? And this really then became NonlinearSolve.jl. But of course we had to do a breaking syntax change in order to make it so that way it could be its own whole library. And that was probably the largest change that we did to the internals of differential equation solvers in a long time. And it was a very major improvement that we then have today, where now there's a lot of other people who don't use the differential equation solvers that still contribute and improve the linear solvers underpinning the whole library. In 2022, then we also started going down this area where, not even just going from things in past papers, but now we understand the research space so much, let's start to develop our own methods. A lot of this ended up being, we were developing our own methods in SDs before, kind of dropped that a little bit to be working a bit more on the scientific machine learning methods, but then in 2022 it really came back with some of the parallel extrapolation methods, where now if you had 200 or less stiff ODEs, these parallel extrapolation methods and these better these better methods for parallelization were the new best method by another 4x, right? So at that point, small stiff equations were really, in the territory we had. There's still more to do in terms of large stiff ODEs. We tend to only get something that's like 2x over sundials, but in the smaller stiff ODEs, we started to get a lot of performance gains for many of the cases. I mean, not every case will be the same. In particular, some chemical reaction equations can be different, but a lot of the smaller stiff ODE cases were handled really well by these extrapolation methods. And also DAE initialization, along with the initializations with event handling. 2022 is really when our DAE story really kind of came together. And we started making the differential algebraic equation domain be something that's quite robust. And I would say at that point it becomes more robust than anything else in the open source space, where the only thing really kind of rivaling that is the tooling that you see from Modelica, right? Because we adopt a lot of the tooling there, and also started doing a lot of research along the lines of this DAE solver space. And then in 2023, we had a lot of the kernel GPU methods, right? If you haven't seen that paper, that was in the new set of methods that we developed. Let's see, how would I find it at this point? Automated translation and accelerated solving on multiple GPU platforms, right? So we had this paper come out, which really showed a lot of really nice results for if you have specialized implementations of solvers that go as GPU kernels, rather than targeting the array form of library. So like PyTorch and JAX, anything that was developed along those lines, they target the array form for GPUs. That way they can reuse the array intrinsics. If we instead directly build kernels that are PTX kernels that are running on the GPU, we can see that we get like a pretty massive performance improvement over what you have in the machine learning libraries. We're talking, like 30x to 40x against JAX kind of thing, right? So that really became like this. The same underpinning for the GPU solvers actually becomes the methods that are good for static compilation. And so this kind of gives us, again, for the small stiff ODEs and for the small stiff non-ODEs, this gives us a major performance improvement there, where that's kind of an area where we dominate quite well. And that ends up being very good for things like Pumas and Julia Sim, which kind of, you have this case is like a major use case area, but also it's just most people write 200 ODEs or less, and so that's kind of been a bigger focus. But now we're kind of regaining that focus to very large equations again. So then in 2024, there was kind of a rework towards nonlinear solve integration. Actually, more of that nonlinear solve integration is happening in 2025. There's new research on some new methods that actually should improve that. Every non-stiff equation should get like 5 times faster. Every stiff equation should get like 50 times faster. Hopefully that'll all be done by this JuliaCon, and that should be the JuliaCon talk that I'll give. Right. So again, if you kind of want to summarize this, the 2016 to 2021 timeframe was kind of like this. Let's build up everything that everyone's had before. Let's make sure we can match it bit for bit with little twists on it. But after we start doing these little twists, we start saying, okay, methods that get better parallelism, methods that better nonlinear solvers, and then entirely new sets of methods, which again, they'll be a fun topic. So that's for a future talk. But we start saying like, okay, once we've learned what everyone had done before, all of our new methods end up being, having a lot of meat to them since then. But now with that, this kind of leads us to the topic of ordinative diffeq v7. Again, we keep on adding more and more and more solvers to the same library. And so then that means that the time it takes to load the library got larger and larger and larger. And that also meant that, some of these methods are pretty large, right? Especially the extrapolation methods and the Rackauckas-Chebyshev methods. And it just, not everyone needs all those methods, right? Again, we have some specialized methods where, parallel extrapolation methods are good if you have a lot of cores in your computer and you want to solve stiff equations of 200 equations or less. All right, that's a very specialized one. We don't even use it in the default method because it's like so specific that, why add another default when it's, it gives you a 4x improvement, but for the default method, you're not going for what's the fastest. We're just going for something that's good enough and robust, right? And so, we don't even use it by default. You have to opt into it, yada, yada, yada. So why are we loading it by default every single time? And why are we loading, this whole setup with, 16 cores and everything just for the people who need this one specific method and choose it? And so ordinary DiffEq v7 really was this kind of split into solver sublibraries, which again, this was this change which had been happened, right? We've already done the split into all these solver sublibraries, but right now most people probably still do using differential equations and using ordinary DiffEq. And right now, what those actually do, let me just kind of show you the code on this, right? If you do using ordinary DiffEq, what it does is it does using ordinary DiffEq core, which is the basic library it's all built on, using the differentiation library, the nonlinear solvers, extrapolation, so it just imports all of these sub-libraries just because this is non-breaking, right? It's not breaking for us to move code around, so we've just moved the internals of the code around, so that way you don't notice that they've moved. But in reality, all of these solvers are in sub-libraries now, and what we want to do in the near future is we just want to make it so that way ordinary DiffEq is not a library that has all that much. It should just really have the default method, and if you want to use other methods, then you go to the library that has that method. If we're going to do that change, then that is of course a breaking change, and that would be the breaking change for ordinary DiffEq v7. Now, for most people, that will actually not change anything because most people just use like 5 solvers. Most people use sit5, one of the Werner methods, one of the FBDF, QNDF, or one of the Rosenbrock methods like Rodos5, Rodos5p, right? So we'll keep those methods in ordinary DiffEq. That'll make it so that ordinary DiffEq is something that imports like 5 of these libraries, and then the other ones are discarded. And we still would actually recommend that most people don't use ordinary DiffEq directly, but just use the solvers that they want to use. Reason for that is that you'll just get better load times, right? We'll still leave ordinary DiffEq around, especially with differential equations, because it's much easier to document, this is the way the differential equation solvers work. These are just like one little change to the solvers that just says use this solver instead. They're different libraries because we want to decrease the amount of loading, not because they're actually different code, right? And so, also the pre-compilation is set up in a way that is solver specific, yada, yada, yada. So we will very soon do this cut, so that way your ordinary DiffEq will load a lot faster, but then we also recommend that you just use the fastest loading form, which is just grab the solver that you want. Now note that we're actually trying to improve this within Julia itself. Let me pull up the piece on that. This is the thing on mono repos. If you're interested in this, you might want to read this whole this whole issue. The whole point of this issue is that, again, the reason for the split of ordinary DiffEq is not because it's actually good to have these as separate packages, right? We keep them within the same Git repository because these codes are so intermingled that we need to update them together. The reason why we do this is because it's actually for making sure that we just improve the loading times of people, right? There's no reason to load every ODE solver if anytime you solve an ODE, you only call one, right? And so we have this kind of ask to the compiler team. This is now picked up by the Julia Hub compiler team. There's been a larger discussion, yada yada. You can read all this if you're interested. But what the goal of this is that we plan to make it so that way you can have some form where you say using ordinary DiffEq, but it doesn't load all the solvers by default. And then you can load sub-libraries, and those sub-libraries would grab you the one solver. And importantly, all of them would be on the same version, right? The main downside to the solver split form is that every single solver library has its own version, which gives you this kind of versioning nightmare of being able to be like, okay, what version are you on BDF solvers versus what version are you on the Sturk solvers? Do they match in your manifest? Yada, yada, yada. It's kind of a mess, right? But the goal here is that if we have a single library that has sub-libraries that are loading on demand, also have separate dependency management and separate pre-compilation, then all the issues with load time are handled. And so there's suggested syntax and everything going on in this library. So we can say like, using ordinary diffeq, hashtag, using main package, : sub package, right? And there's all these different questions of, okay, should they have different project.tomls? How do we maintain the dependencies between them? So the story's ongoing, but, they've also gotten people chime in to say CUDA.jl is very similar in the fact that CUDA.jl has cuTensor, cuDNN, all these packages that are really tightly coupled with CUDA.jl. So, how can we split this up? So this is a major change that will be happening in the Julia open source ecosystem. Until then, we have different packages for each of the solvers, and they're versioned differently. That is not how we intend it for the long term, but it gets us the faster startup times and the separate pre-compilation for now. Parallel. We get parallel pre-compilation because each of the solvers, compile separately, and then we'll cut down on what ordinary diffeq actually has, just to make it so that way it's simpler. For most people, you just use the same 5 algorithms, and you'll just see that your load is faster, and they'll never learn about all these sublibraries. I assume that most of the people who learn about these sublibraries are the people who are hardcore enough to watch this video, which is a smaller set. But then we'd hope that, we then would have an ordinary diffeq v8 that comes around sometime, hopefully a year or two in the future, which is using the new sublibrary feature that once is built into Julia, that then makes it so that we just do using ordinary diffeq. You have one version for all solvers. They're all kept in line, but you still get this advantage of quicker startup times because you're only loading solvers on demand. So that's the ordinary diffeq v7. Hopefully that makes a lot of sense to you. That was a huge breaking change that we did, but now, all the major changes there are completed, so yay. And then after we did the completion, there was like 2 months of mess that we had to clean up because, again, if you move around about 1 million lines of code, a few issues will be found on the edges. I think we've mostly worked out those edges at this point, though. So we're pretty happy with the split at this point, other than the fact that the maintenance is a bit odd. Sometimes you have to bump the versions of 20 packages together, and they have some release issues as it's happening. We're very sorry about that, but we're hoping that this is only a short-term solution until we get the longer-term solution, which is a full monorepo subpackage submodule solution in PKG in the Julia compiler. So a thumbs up this issue if you want to see the solution there. I think that's probably the biggest development issue we have right now, but we're working with the folks that would be able to give us a solution here. Okay, so simplified timeline of the other core solver packages, right? What do I mean by the other core solver packages? For example, nonlinear solve, linear solve, integrals, and optimization, right? Let's talk about what happened here, right? So again, in 2016, we started building event handling tools into the ordinary differential equation solver. And how do you do that? Well, event handling has to solve root finding problems to find where the event happens, right? We started doing that by using Roost.jl. We started using implicit solvers that use NonliarSolve.jl. But we started finding all these performance issues in these, right? So we started saying, okay, instead of using Julia's built-in linear solvers, A/B, we're going to build our own internal linear solver system. One of the big reasons is because we need to be able to switch between umfpack and KLU, which are different sparse matrix solvers, right? If you use sparse matrix A/B in Julia, also in MATLAB, also in SciPy, it always goes to using umfpack. There's a second solver, actually also in the same C and Fortran code that everything pulls from, sweet sparse, that is called KLU. It is slower for a lot of cases that have, these kind of sparsity patterns like PDEs, but if you have an almost random sparsity pattern and your matrix isn't sufficiently large, like a circuit modeling problem, KLU is actually faster. And it turns out that for most ODEs that people were running, it was actually faster because most people's PDEs were not in the, million by million range. It was in the 10,000 by 10,000 range, which is still actually, even for a sparsity pattern like a PDE, a lot of those are actually just faster with KLU. And so we started creating our own linear solver backend so that we can default to KLU, but then switch to umfpack when we decided that we need to, and yada yada. This is a lot of the work to make the internals just faster, right? And then we go and we see like, okay, actually OpenBLAS, the BLAS library that we use for LU factorization, isn't actually as fast as it can be. And so one of our contributors, Yingbo Ma, created this recursive factorization.jl along with Chris Elrod, who did loop factorization.jl. And so for LU for factorizations that were matrices of like 200 by 200 or less, we started using our own LU factorization library, right? To kind of back this up, if I go to the benchmarks, that's SciML.ai, you will then see that inside of here there's LU factorization benchmarks. These are very different on different chips and different cores, but you'll see here, for example, that the fastest library here is RFLU factorization on these chips. And so this is our built-in library. And you can see that, OpenBLAS, which is this blue line, right? We get almost like 50% performance improvement. And for a lot of stiff ODE solvers, most of the time is in the LU factorization. And so this is actually just directly translates to a 50% performance improvement on this chip. Now, it's actually very highly chip dependent. Let me kind of pull up the information here on that. So here I'm pulling up a side talk that I gave before in Eindhoven on linear algebra for industrial applications that kind of goes into some of these details if you really care. So it's kind of like almost a tangent, but again, I'm on my own timeline, so I can have my own tangents, right? Again, I showed you the LU factorization result. This is on an AMD EPYC chip. AMD EPYC is the server chip created by AMD. And so you kind of find that MKL, which is the Intel-based BLAS, is the slowest. It doesn't work very well, specifically on the server chips. It turns out that on other AMD chips, like AMD Ryzen, ends up being one of the fastest methods as you get to larger matrices. No conspiracy there, right? Oh, just so that we're all clear, this is measuring G-flops, so higher is more flops per second or faster solving of LU factorizations of size n by n, where n is given in the x-axis, right? So if you're on a AMD EPYC chip, then MKL is the slowest, and our this recursive factorization.jl is then the fastest. Whereas blue, which is the Julia built-in default, which is OpenBLAS, is the one right in the middle here. On AMD Ryzen, our recursive factorization.jl can be quite a bit faster, about 4 times faster than OpenBLAS, depending on matrix size. If you're on Intel, then MKL, which is again the BLAS chip that is made for Intel libraries, is about like 2 times or 3 times as fast as using the Julia default. And if you're on Mac, then Apple Acceleration is an LU factorization that ships with the M series chips, and you can see that that's also the fastest in that domain until you get to a certain size, right? So Julia defaults to OpenBLAS. Actually, Julia defaults to this, and then also SciPy defaults for this, and ours. It's just like the standard open source thing is you just default to using OpenBLAS. But we realized that on stiff ODE solver code, you can get quite a bit faster using these other libraries, but it's very chip dependent. So we built our chip dependent model that would actually look at the CPU version that you had and then choose the defaults based off of the CPU version that you had. And then we also had our own one built, our recursive factorization.jl, that ends up being the fastest on many AMD chips, and also in some ranges for even Intel chips, until you get to about 150 by 150. So that was a development that happened in, say, 2019 to 2020. And then also all the stuff on the sparse matrix solvers, right? So if you have a one-dimensional partial differential equation, this is an n by n sparse matrix that was created by the one-dimensional Laplacian. You see that KLU is the fastest, right? So this is time and n here, so lower is better now. KLU ends up being the fastest solver across the board for 1D PDEs, but for 3D PDEs, until you get to about 1,000 by 1,000, KLU is the fastest, and then Paradiso ends up being the fastest, with OOMFPAC being right. But this red line, if you ever do A/B on a sparse matrix in any open source language, they'll always give you UMFPAC every single time. This is the default that it chooses, which is when you start to look at this, you say, this is insane. We can get so much more performance out because this is log scale, right? So this is a 10x difference is right here. And so you're seeing some 3x performance gains on a lot of different cases from this. this. And so, and so that's just even just looking at the linear algebra. And so that's why we started building our own linear algebra interfaces, right? So we changed the default for small ODEs to being recursive factorization.jl. We made it CPU dependent. We also made KLU versus umfac. We did all these changes because, this is the right thing to do, and it's a morally correct thing to do. And then integrals.jl was then established as a spin-off library because we needed it for other projects. NonlinearSolve then spun off because we started implicitly building new root finders inside the differential equation solvers to fix performance issues with roots.jl and NLSolve.jl. So those spun off to different libraries. And then in 2021, we say, okay, like these are libraries that are not just for the ODE solver. It's linear solve and nonlinear solve, and let's make them so that way other people can use them as well. And so then in the 2021 to 2023 timeframe, they mature, they become regular names, they get their own JuliaCon talks, their own workshops, their own documentation, and become standard parts of the libraries. And so that's why I say it's transitioning medium to high, because in the 2023 timeframe, you kind of see their maturity. Though, again, if we look at the definitions here, for maturity, right? They reached their maturity in 2023, but in 2024, 2025, that's when we're doing they got their JuliaCon talk, they're getting their workshop, they're getting their special documentation, and they're getting their own focus inside of MIT graduate courses. All this like material around it that building up, right? They haven't really gotten all the material yet, even though, for example, Linear Solve has gotten its JuliaCon talk, NonlinearSolve Solve has gotten its JuliaCon talk, but they haven't gotten specialized workshops and all that yet. So they're in that transition phase now of they were medium right in 2022, like they worked, but now they're starting to get the pieces around it to say, okay, they work for everybody, kind of change. Now, the big change in 2024 was at nonlinear solve, right? And we had started building off like all these trust region methods and everything, but it started becoming split from DifferentialEquations.jl. And so then we kind of had to do some work to make it so that way DifferentialEquations.jl then starts to use nonlinear solve as a backend. And that's actually a pretty deep topic because you need to specialize solvers quite a bit to be used in differential equations because you're not solving different nonlinear solves every single time. There's like a sequentiality to it. There's some relationships between the ones that you're solving. And so making it so that way you can robustly reuse Jacobians and certain features like that need to be built into these differential equation solvers so they could be accessed through the differential equation solvers. And then also one of the big things is that these also started gaining enzyme rules and chain rules. So, before we had differential equations got set up with the machine learning libraries, but then linear solve, nonlinear solve, integrals, all those need to get set up with automatic differentiation support as well. And then we had the simple X solvers, right? The simple X solvers where these solvers made compatible with GPU compilation. Okay, and then we had integration with differentiation interface. So then, as I mentioned, right, we have this whole setup where we say, okay, well, maybe even all this automatic differentiation doesn't also need to be, especially with the sparse automatic differentiation and such, it doesn't need to be a thing within SciML. It could be a more general tool. So just like how we spun out these linear solvers and nonlinear solvers, we then started working with groups to spin out everything that we needed for the differentiation, automatic differentiation, switching features and such, and the sparsity of the automatic differentiation. This then becomes differentiation interface. And then we start to retarget NonlinearSolve.jl, DifferentialEquations.jl, and etc. to start using differentiation interface under the hood. That's actually not completely done yet as of the time of this discussion, but you can see that it's very, very far along. I'm sure that this will merge, and then we'll have some things that a week of stability gathering. But we're a few hundred comments into 261 comments into almost getting this merged 2 days ago. So. Yeah, so that move to differentiation interface has been a big change of 2025, and it's almost done at this point. The other thing is now using a lot of these tools like AlloCheck and Dispatch Doctor, Jet, and these things to make sure that our code is non-allocating and is free of runtime issues, so that way it can be used in static environments with the tooling for binary building, right? So going beyond just the ODE solver, doing that with DiffyQ GPU, but then doing that with NonlinearSolve GPU, LinearSolve GPU, optimization GPU, and etc. Right? The point is, making NonlinearSolve, LinearSolve, integrals.jl, all those libraries have as much of that outlying ecosystem as the differential equation solvers have had. And then the next one is optimization.jl. So optimization.jl lives in a pretty interesting space because, there's other tools that have done optimization in Julia, right? Especially one big organization being Jump, right? Jump is an organization that has built fairly good optimization tools in Julia. And so since the very beginning, we said, we don't need to work on any optimization libraries because there's groups that do that, right? First of all, we just said, okay, if we want to make parameter estimation easy, well, a big thing is that we need to actually be able to use more than one optimization library because NLOpt has some advantages, Optim has some advantages, Evolutionary.jl has some advantages. So we built DiffyQ paramestim.jl, which is a parameter estimation for differential equations library, which built cost functions that made it easy to multiple dispatch target different optimization libraries, right? And then that kept on growing because Flux.jl had its own solvers, and so we wanted to start putting differential equations mixed with neural networks. We started being like, okay, we need stochastic gradient descent and atom method. So DiffyQ Flux starts to have its own interface that is really good for targeting these machine learning types of optimizers and mixing those with Optim.jl. And then we go, okay, well, actually, we just need to. What we really need to do? We need to have a way to be able to find an optimization problem and then just switch between the different solvers. This is literally what we did in differential equations. This is literally what we did with stochastic, with linear solvers and nonlinear solvers. But we need to do this for optimization. And, the reason why we need to really do this for optimization is because even though the Jump existed, it wasn't really an interface where, general Julia code could be given as a problem and then you switch between solvers. It was merely made to have its modeling interface, right? There is MethodOfLines.jl in the Jump ecosystem, which is kind of like this back end, but it's not really made so that way people could just the average user is not supposed to be using and calling MethodOf.jl directly. It's kind of there for Jump developers. And so we decided, okay, we need to have a interface library, just like DifferentialEquations.jl, but for nonlinear optimization. And so that became GalacticOptim.jl, where it was named Galactic Optim because one of the big use cases for it was to have one interface over all the global optimizers, right? So NLOpt, Evolutionary.jl, BlackBoxOptim.jl, MetaHeuristics.jl, Multi-Start Optimization.jl, were all these different ways to do global optimization. If global optimization solvers are really finicky, so we need a easy way to be able to switch between them, for the benchmark between them. And that became GalacticOptim.jl, which was a joke because, what's bigger than the globe? The galaxy, right? So, and that's pretty funny, right? And then in 2021, it starts being like, okay, this is actually not just about global optimization, because now we also have these local optimizers from the DiffyQ Flux library, right? Let's get rid of the internal optimizers of DiffyQ Flux. Let's get rid of all the specializations of DiffyQ paramestim. Let's take this Galactic Optim that we started already building this interface for and just make it over all optimization libraries, right? And that became optimization.jl. And because this was early on, we already had this foresight of, we'd have to do this solver splitting of ordinary DiffyQ. We actually started here with different libraries, so that way it was kind of already pre-split, and that kind of became the way that ordinary DiffyQ, NonlinearSolve.jl, and LinearSolve.jl have now all split to separate solver libraries. It was actually showcased here in Optimization.jl first. And then we also added MathOpt interface.jl bindings, right? So it was like, MathOpt interface is not necessarily made to be a human readable target for the average user to be able to hook into the solvers of Jump. But optimization.jl is a thing where people give it, Julia code that they call solvers. Well, if we give it Julia code and we can hook it into MathOpt interface for people, then we get access to all the solvers of the Jump ecosystem. And for example, one big one is the IP-opt wrappers. So that all happened in 2022. So then we became, I would say, pretty integrated with the Jump ecosystem where, there's different ways that the Jump people want you to model. We have different ways that you model, but we both hit the same underlying solvers under the hood, at least for all the solvers that they've wrapped through that ecosystem. And then what we started to do also as well is that, for nonlinear least squares problems, and it turns out that using nonlinear solvers is better than using optimization methods. And so we started having specializations for nonlinear least squares problems. That's a huge topic. Actually, this can be one of my next JuliaCon talks, so check out JuliaCon if that didn't make sense to you. But basically, you don't want to use a standard nonlinear optimizer if it's a least squares problem. And then we also had a lot of derivative-free methods come from Prima, which is these new Fortran libraries that got put in, and then also sparse hashing support and enzyme integrations to make it so that way your Julia code is just able to scale better and do more. Started again, like we always start this off by wrapping everything, wrap in the differential equation solvers, wrap, linear solvers, wrap, and then we go, oh, actually we could do this better. Oh, actually we could do this better. We can do this better. So in the optimization space, that's started really happening in 2024, where the Turing optimizations and modeling toolkit tend to give you symbolic numeric better optimization code. The implementation of augmented Lagrangian, LBFGS, these are added then to optimization.jl and become the new default solvers because they outperform optim.jl and some of these older methods. And then we start actually building some even new solvers, right? I think that there's some that haven't even been widely announced yet. Let me see if I can find it. PSOGPU.jl. So we have this, like, for example, PSOGPU.jl, which is a particle swarm method that it is able to be accelerated on GPUs. We have a paper that shows how this is like 10 to 100 times faster than a lot of other black box optimization methods, yada, yada, yada. We're actually going to do a new version of the paper in the near future. So we started getting in the space of writing new global optimization, specifically within global optimization, because that's kind of like this space I think is not really well rounded out by a lot of other ecosystems. Global optimization with GPU methods and really handling a lot of that. So a lot of the integration with modeling toolkit, multi-objective optimization, global optimizers, and a lot of other interesting cases here. So this I think sometime in the 2025 timeframe, 2026 timeframe, we can call optimization.jl to be medium maturity. I think that if you look at NonlinearSolve.jl, right? If you look at the different libraries, like DifferentialEquations.jl, back in 2017, we wrote the paper saying, like, yeah, this is now the best for this, and this. And we kept on working on it, of course, making new better solvers. But we're kind of in that regime of like, yeah, we know what we're doing. We have this down. This is the best thing ever, 2017, right? NonlinearSolve.jl got that paper in 2023. We started working on it saying, like, yeah, look, this is, let me actually pull up the paper just so that way we're on the same page here. With NonlinearSolve.jl, we're able to start saying in the time frame of 2023, finish writing it March 2024, where we say, yeah, like if you compare this to existing software, like, both NLSolve, but also all the old Fortran methods and everything, we're able to show that we're faster, more robust. We have automated stiffness detection. It's more robust than what's in Sundials. It's more robust than the Fortran methods like MinPack. And then we're also adding in all the stuff with PET-C, yada, yada. So we're able to say, like, we've hit something big, right? LinearSolve, we hit something big. Integrals.jl, it's all just wrap methods, but, it's also at that level. Optimization.jl, we're still finishing up the wrappers in 2024, right? Getting our first real beyond the basics in 2024, 2025. So it's less mature than the other libraries, but it's getting there. It's getting close. It might actually need some kind of bigger breaking change, and because we're changing things with the differentiation interface and such under the hood, but we also are missing multi-objective optimization problems right now. So there's still some bigger things to be done in optimization.jl, which is why it's labeled as a maturity level low in comparison to the other solver libraries. But it's getting there. I think the 2026 timeframe will mark its medium, where then we'll be able to say, like, yeah, we have some of our own pre-built optimizers, look, they're so much better for this reason, and, but we still wrap everything else. Here's the set of benchmarks. We'll be able to showcase that whole thing that we do for the other libraries. We're just not there yet for this one. All right, and that marks the discussion for the solvers, and we're an hour and a half in. So that was I can't believe I planned that for half-hour JuliaCon talk. So, okay, the symbolic modeling interfaces, what do I mean? So when we look at Julia, the Julia SciML ecosystem, right, we have all these solvers here, but then another big aspect of this is the modeling tools, right, especially modeling toolkit and symbolics being some of the largest, most, maintained and most used libraries in their own rights, right? The modeling toolkit ecosystem is still in that low to medium maturity level, right? It's not as mature as the solvers because A, it started a lot later. It started getting its main focus a lot later, but also B, there's a lot to do with it, and it's much more open-ended of a problem. Okay, in 2016, we had the first versions of parameterized functions created. And parameterized functions.jl, and then set up SimEngine as a backend. So it uses, it had this macro interface. Let me kind of show you this because it hasn't actually changed as well. Parameterized functions.jl. Right, it has this macro interface where you say, okay, add ODE def, and you give it a differential equation definition, and then it uses that macro interface, and it does some cool simplifications and some cool Jacobian building behind the scenes to give you back something fast. At first, that was all done with SimEngine.jl, which is this, faster SymPy rewritten in C++, for that, right? And DiffyQ Biological then created a similar macro on top of that, right? We now call that Catalyst. You go to catalyst.jl, you'll see that, this catalyst.jl, has this at reaction network where then you write down these chemical reactions and it builds this representation of a system to simulate from these chemical reactions, right? See, that's actually similar in many respects to parameterized functions, right? There's kind of like a similar genesis around a similar time, and both were using SimEngine as the symbolic backend under the hood, right? But then we realized, okay, Pumas also was very similar too. It also has a macro that defines, like this macro syntax for defining an ODE, and then we do these specializations, yada, 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 on the build ODE. So after you do something 3 times, you start to say, okay, should we actually just have a library that is good for building ODEs from symbolic definitions, right? And that became known as modeling toolkit.jl. It was first called SciComp.dsl.jl, Scientific Computing Domain-Specific Language. But then, it got a better, worse name. So, okay, many symbolic backends were tried. So we tried SymPy, we tried SimEngine, we tried Reduce. Reduce is the Lisp, common Lisp-based symbolic language. SymPy is the one in Python that is dog slow and terrible. At least it implements some things, but yeah, it's like when we changed it, it's like 100,000 times slower in a lot of cases. And then there's SimEngine, which is actually pretty good in terms of performance, but it just didn't have the capabilities to be able to, incorporate any new functions we wanted and have the flexibility. And so we started building an internal symbolic engine, right? So we started modeling Toolkit, which had its own internal symbolics engine. And actually there was a student at the time, Harrison Groden, who helped with a lot of the genesis of that before this had helped out by Shashi and Yingbo to then become the later stage piece, right? So then in 2019, we started being like, okay, a lot of the reason for modeling toolkit is to do symbolic things, but now we need to take symbolic code and generate code and compile it. And we ran into a lot of issues with what's known as stage compilation. And so then the real genesis for making this project into reality was runtime generated functions.jl, which is a fantastic library because what it lets you do is it lets you take a Julia function or a Julia expression and then create the function for it and call it in the same world age, right? Or call it within the same function. Now, if you do this with just eval, you get a world age issue. There's a whole discussion as to what world age means, why that exists and everything. But this solves the world age issue by a very weird trick. It lies to Julia's purity checker because it checks for code inside of a dictionary based on you don't need to know how it works. But what this meant was that now we can now generate code as we need it and be able to optimize it as needed. And so we can run the compiler as part of we can basically run the compiler at runtime to then switch back to compile time, right? And that stage compilation solving meant that we're now free to write our own general things which use the JIT compiler and use Julia's compiler as part of it. And the modeling toolkit then really took off as a project at that point, where then also Symbolics.jl was separated out to its own library in early 2020. So then this internal symbolic backend of modeling toolkit became Symbolics.jl, and the modeling toolkit became the modeling interface that was built on Symbolics.jl. Then we had the PDE systems added for Method of Lines and NeuralPDE.jl, so all the stuff with physics-informed neural networks that kicked off a lot of funding. DiffyQ Biological was renamed to Catalyst. But then the real big change was, again, if we kind of go back here to these, organizational moments. One big organizational moment was in 2021, where we decided to do the Julia Sim project and really started to take on, the Modelica tools and the DAE solvers there. And that needed a backend that was similar to, say, Daimola. And Modeling Toolkit, already being this kind of compiler and interface for modeling, really became the thing to do that. And so Modeling Toolkit then got all the support for A-causal modeling, Pantelides algorithm, and DAE index reduction. So the tearing, alias elimination, all those things that you find only within really the Modelica space, Julia Sim really made it so that way Modeling Toolkit would get all that. And then Symbolics.jl became a spin-off library for the symbolic cast, so that way we can kind of maintain the two separate projects together. And then we started building other things on top of these libraries. Right? Structural identifiability in analysis was built on Modeling Toolkit. And then we had all the file readers like SBML readers, CellML readers, BioNatGen readers for the pharmacometrics community, because also Pumas is using Modeling Toolkit together as well, right? So this whole ecosystem of, what about having, just one backend that we represent and optimize the symbolic ODEs on? Something became something where we just say, okay, now we have an entire group that's building out tons of optimizations on it, and then other organizations are building readers to that file format that then use the same optimizers, and so this economies of scale started building around Modeling Toolkit. And then we started to say, okay, this actually doesn't need to just be about differential equations. It could be nonlinear solves, SDEs, optimization. And so Modeling Toolkit grows beyond like the Modelica space to say it's now just a general system for representing representing equations and optimizing equations before you would solve them. In fact, we start calling this symbolic numeric computation, which is a small field that did exist before, but now the Julia Lab is one of the big players that kind of is really creating a lot of the code in the symbolic numeric space. But then we started looking at, alternative ways of compilation. So using a symbolic library has some downsides in terms of the code size. So we started building some alternative compilers that were doing some direct-to LLVM and direct-to-C compilation, specifically for also targeting embedded devices. That's another reason for doing this. And so then, what we started saying is like, okay, now that we've had this sprawl of the symbolic tooling, let's start defining interfaces so that we can start to become more exact, right? So in 2024, the symbolic indexing interface became something that was this crucial new change. Symbolic indexing interface.jl. If you haven't seen this before, it is now the library that defines how the symbolic indexing works. So for example, if you solve an equation with Modeling Toolkit and you do sol of x, you get the time series, right? This is a feature that we just kind of added, and it just became like the core way to use Modeling Toolkit. We're like, this is so cool, but its definition was kind of undefined. Like, what is it to be a symbolic index provider? What is this actually doing? If I wanted to have a new type that implemented this indexing, how do I make sure that it supports this indexing? How do I make sure that plotting knows how to use it? What are the definitions on this interface, right? And so we had to actually start saying, okay, for symbolic indexing, this is the interface. For symbolic interfacing, this, everything needed an interface. And once we started putting interfaces to everything, of course, we started to get this simplification in terms of, all the edge cases start being cut out, and we start being able to really expand what we do and make it a lot more refined. And so in 2024 was this refinement period. 2025 ends up being this bug fix period to this refinement because, anything that's a major edge case, we started having to work out in Modeling Toolkit v9. I think that Modeling Toolkit v10 will be then in this space where initialization interfaces are here, clocking interfaces for hybrid systems are here, and all these interfaces are well defined, and we need to now just chop out, in Modeling Toolkit v10, all the old ways of doing things that are not robust and force people into the robust interfaces. And so I think that, we're calling this in the low to medium range. I think that this Modeling Toolkit v10 will really be this point of starting to get to the medium functionality where we say the core features are there. Now we're just creating passes to make things better and better. That should be happening in the late 2025 to 2026 timeframe. And with one of the other things I'm really doing at this point being to expand out Modeling Toolkit to more and more PDE interfaces, connecting with Ferrite.jl, connecting with Trixie.jl, and then also working on a lot of performance improvements, right? Because what we've been able to do with Modeling Toolkit is make it a very good symbolic backend for handling a lot of these differential equations. One of the things you start to see, though, is you start to see people pile in, partial differential equations, and they say, oh, this thing is not so great for creating codes that have 1,000 lines in the generative function. And so we started building this alternative compiler, this Julia Sim compiler, where it would actually have this own internal intermediate representation that it would do the structural simplification on. And it was able to take code that would be scalarized in the symbolic form and turn it into looping code, right? Because there's no native representation for a loop in a symbolic system, but there is a native representation of a loop in intermediate representation in code, right? So it's kind of extending what we did symbolically to a code representation, and you can automatically switch between them. This is Julia Sim compiler, and you can see that there's orders of magnitude of performance improvements and things like battery models that are these larger PDEs. And then also like these internal linear solver optimizations where you can pre-write solutions to linear solves, and this ends up becoming a big optimization in multi-body libraries. Right now, I will say that since the time of the slides, Julia Sim compiler has actually been discontinued because there's a new framework that we're doing, which is called DAE compiler within the Julia Sim team. And Julia Sim DAE compiler will get a lot of these. It has a lot of these ideas, but in a way that's more easier to maintain than Julia Sim compiler, which is more directly written to LLVM code. DAE compiler will make use of more of the Julia compiler, which will make it easier to scale the developer team and maintain and such. So these performance benefits that we saw from 2023 to 2025, you'll see that Julia Sim compiler did a whole lot of really nice things and suddenly was discontinued, but it's because there's a new thing that'll be coming out soon. And so this kind of spawned this whole, again, this is like a whole research area that kind of grew in a whole compiler development area. In symbolic numerics, which kind of is now one of the bigger areas of the SciML organization. And you don't really see other organizations that have like a strong, major research, other open source organizations with, 100 contributors and such that have a huge symbolic numeric situation. I don't think that there really is any. So this is really where a lot of the research and innovations going on right now. All right, so just to pull out and highlight some of the things that happen in symbolics.jl a little bit, right? As I mentioned, we tried a whole lot of backends like SimEngine, which wasn't flexible enough, SymPy, which by far not fast enough, and Reduce, which just had a lot of issues as the symbolic backends to Modeling Toolkit. But finally, we said, okay, we need to just build our own backend that does what we need. In 2021, it was split out to being its own library, so that way it became a whole computer algebra system, which is also then being used as the backend for Modeling Toolkit. And then we started working on a lot of the performance things like the unitype or sum representation, which is kind of a representation pulled from SimEngine with a few extra tricks. We started writing our own integrators, right? So symbolic numeric integration.jl is a symbolic integration library. We started creating a lot of symbolic arrays, right? Symbolic arrays then allow you to be able to represent PDEs with just, without having to write out every scalar equation. That was a big change. And also registration of array functions, right? So being able to say, hey, in my equation, I have a neural network call, right? And so then also these things like Grosvenor-based libraries, translating to and from SymPy, so that we could call functionality that's missing. Right, it became a symbolic library, kind of like SymPy. It has Grosvenor-based libraries and all these, but it has this kind of focus on being able to represent big array equations and being able to do code gen in a way so you get very fast code. Right, whereas like SymPy's LambdaPhi is rather slow. This is for building non-allocating high-performance equations that auto-parallelize post-symbolic post-symbolic transformations. Now in 2024, then we started being like, okay, now we really got to improve the performance a lot. And so a lot of this was by reducing dynamism, closing the type representation, not sorting by default, hash consing, and a lot of this is actually ongoing. So there's a lot of performance improvements that are ongoing, and we're actually, from the Julia Lab, going to have a paper in the near future about a lot of these optimizations. And so we're kind of see SimEngine as the gold standard for performance. We don't quite match it yet. We match it in some respects, but not in all respects. But we have an ongoing set of projects to be able to get there, where we're trying to hit that same level of performance while still giving us the generality in terms of like having registerable array functions, especially a lot of the array functionality that SimEngine doesn't have, right? So have the generality and the array functionality, but have the performance of SimEngine is this goal that we're trying to meet. And then with the array functionality, you start going, okay, you have to be able to differentiate arrays. So symbolic tensor calculus, these are some of the projects that we're then saying are the near future projects, especially for GSOCs. Symbolic equation solvers actually got completed in that last summer. So if you go to symbolics.jl, you go to symbolics.jl, you'll now see that there is this symbolic solver section on symbolic solver, where you can give it a set of equations and it gives you the solutions to these equations. And so that was a huge effort. It's a very amazing, robust solver, and there are still more things to be done. In fact, we want to make this so that we expand to be able to solve integrals. We want to make it so that way it solves ODEs, and we want to integrate things like symbolic numeric integration as a separate backend, yada yada yada. So this is kind of the 2025-2026 timeframe. We want to do major performance improvements, and we want to work a lot on the symbolic solvers. And so that's kind of where the organization is going next. And of course, there's many other things you can work on in the symbolic libraries. For the most part, we like that we can call out the SymPy when we need to, even though it's slow. But the symbolic solvers are something that a lot of people are asking for, and we need them to be able to improve Modeling Toolkit, right? Because if Modeling Toolkit as a system can say, let's automatically solve this set of ODEs, get the analytical solution, and then numerically solve this set, right? That becomes a lot better of a system. It's able to simplify out a lot more, and that would be done by the solvers in symbolics.jl. So again, coupled projects, but they're both going towards this big goal of making scientific computing better and better by integrating more and more smarts into it. And so now we're basically 2 hours in, and we're finally talking about the machine learning integration of scientific machine learning. See, but I mean, it is still a major part of the SciML project, but the SciML project has a lot of other pieces going on as well, because what we want to do is we want to integrate with these solvers. We want to integrate the machine learning pieces with the solvers, and that really becomes a lot of this inverse problems functionality. Part of that, of course, is building new optimization libraries, building better solvers, and new solvers that can have the right features like automatic differentiation and such. But then the other thing is actually the analysis libraries and everything that uses, the automatic differentiation tooling, right? So at first we had in 2018 DifferentialEquations.jl, which gave us the forward and adjoint differentiation for ODEs. This made it all possible to be able to take fast derivatives of ODEs, right? And then we integrated that with a lot of the the automatic differentiation libraries, so that way they could do special vector Jacobian products, and this is an important little detail that I think is not really appreciated that much, which is that when you build the adjoint method for ODEs, the adjoint method is basically just calling an ODE solver in reverse. And that does exist, actually. I mean, so sundials.jl does have an adjoint method. But where the real performance difference comes from is that adjoint method uses inside of its definition the vector Jacobian product. And for that vector Jacobian product, if you use reverse mode automatic differentiation, you get like 2 orders of magnitude performance improvement. And this is something that we actually highlighted in one of these articles that we had. Let me kind of pull this out here. Comparison of automatic differentiation. Oh no, sometimes it's hard to get my own paper. Well, you can always search and refine the paper on archive. That's how the modern person works. All right, and what you'll see here is this big difference where, for example, the way that the VJP is computed, right, is it using the AD automatic differentiation V transpose Jacobian seeding, or is it actually just going to be building a Jacobian? And you can see that there's actually this huge difference between them, where you're building a Jacobian versus using the AD VJP seeding, right? There's about 2 orders of magnitude. And this has really becomes a big difference of the Julia SciML libraries versus something like Sundial's, right? Sundial's CVODE does adjoint methods, but it doesn't do this automatic differentiation seeding because that requires the integration with a reverse mode automatic differentiation library, right? Even a forward mode automatic differentiation library cannot do this trick in O of n time, whereas reverse mode can. And this is like the key reason for reverse mode. And so what we show in 2019 is, hey, we can have these adjoint methods that automatically does this VJP seeding, and that gives you something that is much faster than what you get, if you just called CVODE and tell it, build the adjoint problem and solve. Now, I will say that CVODE lets you give it a VJP method, but none of the wrappers that I've seen to higher level code bases actually are able to make use of this. It's kind of a lower level refined thing that even the tutorials in Sundials don't make use of, right? It's actually hard to figure out how to define the vector Jacobian product. It's really definable just through reverse mode automatic differentiation. But because we can do reverse mode automatic differentiation on your F, we can have this mixed version, which is building an adjoint code, where inside of your adjoint code it's using reverse mode automatic differentiation of your F function, and that ended up giving us these wild performance improvements and really kicked off a lot of this organization. So then DiffEq Flux was released with the ability to be able to attach the solvers with machine learning in very nice ways. It automates the adjoint method. In 2021, we then realized that we can integrate better with chain rules, so that way, instead of having to use this concrete solve interface, you automatically get adjoints over solve. And so now you have what you have today, which is that, if you go to SciML sensitivity, right, there is no separate interface for the sensitivity analysis. If you go to the tutorials, you just see, like, okay, you define an ODE and then you solve it. And then if you stick that solve command inside of a forward mode, boom, it works. If you stick that solve command inside of a reverse mode, boom, it works, right? This is because it's set up to be able to do overloads on the solve command for telling it how to do the adjoint methods, right? And so there's no more bespoke interface, and also we started integrating early versions of Enzyme for this VJP. Why did that matter a lot? Because Enzyme works natively with code that does mutation, and so you can see that for standard things like PDE discretizations, using Enzyme for that VJP is just massively better than using, even just for versions of reverse diff. And then, of course, that's massively better than using, forward mode or any way of computing the Jacobian instead, right? And so this ends up being like this state of, okay, we have, for this mutating ODEs that people write, it ends up working quite well, even though there's some edge cases on these libraries, like, Zygote.jl itself doesn't allow for mutating code, but because we use Enzyme for the VJP on your ODE F function, that means your ODE can mutate, and we handle that just fine, right? Now, of course, Enzyme still is kind of growing as a library in order to become more and more mature, so more and more codes can use it. But even then, it made it so that way, even if you use Zygote over mutating code, if that mutation is in the ODE solver, we can handle that just fine, and we get very good performance. And then, of course, with this kind of change that we did for all the libraries, right? Again, right, sometime around 2020, 2021, we said we're no longer just Julia DiffEq, we are SciML, and so we're about doing this for all libraries, not just differential equations. That meant that DiffEq sensitivity had changed, right? DiffEq sensitivity is a library for sensitivity analysis of ODEs, so differentiation of differential equations. But now we had nonlinear problems, we had NonlinearSolve, we had integrals.jl, and so DiffEq sensitivity became SciML sensitivity, where it got support for nonlinear problems, steady state problems, and differentiation of linear problems, and basically being able to do the same thing of put an ODE, put a neural network inside of and differentiate for any of these other kind of solver types, right? That's the reason for the name change. It's now for all SciML, not just the differential equation solvers. And then again, the same thing that always happens. We first implement all the cool things of the past, and we start to realize, hey, look, there's new adjoint methods for more memory performance. That becomes our new best method, and then we have this big review article that kind of showcases all the different things. And now we're actually overhauling a lot of the internal, so that way, again, we set up this thing so that way you can switch between reverse diff and enzyme and everything automatically under the hood. But now we're saying, okay, we don't actually need to have the switcher under the hood just for us. This switcher could become DifferentialInterface.jl, so that way it can work with all these other libraries. And so one of the big changes will be to rework the internals so that way they're more maintained by more groups that are using the same thing, because Turing.jl wants to do the same thing, and Jump.jl wants to do the same thing, and so we'll be giving this common interface to all that, and working with especially Adrian and Guillermo, who's doing a lot of the grunt work on making it so that way we can pull that part out. But then also we're still working on improving the adjoint methods, checkpointing to disk, so that way we can go to large PDEs, improvements on DAEs, and performance improvements and SDEs. There's just this ongoing tail, but I think the big thing again is, one of the big things that's happened in the Julia ecosystem is this focus on modeling toolkit and differential algebraic equations, really handling that out well. There's still some things in terms of the automatic differentiation on DAEs. There's a lot of performance improvements that we've realized need to happen that are not out there in the literature, and so that's then become a major area that we're working on still. And actually, so some of the next papers will be on a lot of improvements for neural differential equations in the case of differential algebraic equations, and new adjoint methods for that, and improving the numerical stability, and lots of things going on with DAEs in particular. So yeah, if you haven't checked out the review article, it talks about all these different adjoint methods. So, we say, like, when people say the adjoint method, they actually mean very different things that have different stiff performances and stability and memory. And so we've really kind of charted out this whole space of these different methods, found some holes, and a lot of our improvements now are happening in the holes where we say, is it possible to have this, stiff performance with this memory performance? And what are the combinations? What are the trade-offs that are fundamental, and what are the trade-offs that aren't fundamental, right? And so that's gotten to medium maturity, because there's a whole lot that's done, but I think that we need to have this differentiation interface part done, and enzyme to get a little bit better before we really call it highly mature, because there's some rough edge cases and such that you could still run into. But I think once we kind of refactor the internals and enzyme gets a little bit better, then I think we'll be able to give a thumbs up to say, yeah, every undergrad could use this. So we're a little, we're getting close there, but still not completely happy with that part. So then the SciML deep learning libraries, right? In 2018, Flux.jl was released by Mike Guinness as the core deep learning library for Julia. And we were able to integrate with that in the early versions of SciML, but we realized pretty quickly that its interfaces were too implicit in parameters, and so if we needed to do deeper changes, we needed a separate interface. This became FastChain. The reason why it's called FastChain is because this fast interface ended up, having explicit parameters, so it was about like 5 times faster than Flux for the use cases by SciML. And so this became an internal library in DiffEq Flux, and a lot of SciML people just used the fast chain instead of Flux, but it was very similar in many respects. For the things that we needed in Deep Pumas, we created this simplechains.jl, which ended up being for small neural networks that were seen typically in UDEs. They can work with static arrays really well and outperform JAX by about 15 times. We had some blog posts on this. And so we started seeing like, yeah, we can do some really nice optimizations for these specific cases. And I think then a real big change that happened was then one of the PhD students at MIT created this Lux.jl, where Lux.jl is effectively the same ideas as FastChain, right? Making it so that way you can pass in the parameters directly, expanding a little bit so that way it had a nested name tuple form that worked well with component arrays. Basically just solved the version of FastChain, except made it an entire library, right? And if you go to like Lux.jl now, it's a full, complete library with a very nice documentation. And we go, okay, we don't need to carry around this fast chain thing anymore. We have an entire deep learning library that is purpose-built for SciML utilities. And I think it's actually better than Flux for a lot of use cases, but you can argue that yes or no. But, and then we get rid of fast chain and all that, because it then becomes this full Lux system, right? And so Lux as its own starts kind of taking off as a deep learning library. In some respects, being adopted more in some domains than even Flux, and that makes it so that way all of the different layers, things like attention layers and all that, be implemented there, and they all work well with SciML because it's a whole deep learning organization for that. So it's kind of like it becomes a sister organization, I would say, of SciML, because it was started by one of the students in the Julia lab working on SciML tooling, but now it's become its own whole project in some respect. And so in 2023, we took the change of removing Flux.jl from all the documentation, using Lux everywhere. That got us a lot of performance improvements, a lot of correctness improvements, a lot of better error messages, and a lot of the complaints of the earlier form. I'm like, oh, your error messages are weird. Some things are underdocumented. Yeah, error messages are weird underdocumented because we're using this like little fast chain thing, yada yada. Scrap that, scrap Flux, make it all Lux. And so then it really kind of it was a sea change to the interfaces we had there. And then, of course, in 2024, the ability to mix Lux and Enzyme makes it so that way, suddenly we can start to not just use Enzyme inside the ODEs, but also for the ODEs that have the machine learning libraries in there. That was a big change in 2024. And now the big thing is Lux, neural operators being rewritten to Lux, and also using Reactant. Reactant.jl is now the framework that is using the underlying things of Enzyme to be able to compile much faster neural network codes. And I don't want to steal the thunder from Billy and Avik, but it's much faster than things like JAX even, and so it's becoming like I think it's really just becoming the premier Julia deep learning library. But its development into style then works really well with SciML, and so this is kind of like a pairing kind of made in heaven, and that's kind of what's kind of happening in the 2025 time frame. And in 2026, we'll start seeing just a lot of other deep learning implementations on this, like things like LLMs and such, start to come and that are native to Lux, and then that makes it much easier for SciML to interface with all these different tools. So that, again, this isn't quite SciML, but a lot of people who are the same maintainers, the same students who've worked on this, have now been the ones to build out this space. And they're going to be getting longer term positions to build out the space even more. And so I think that this is really, really a nice development where, the deep learning libraries at first were kind of like a tag on little thing, but now they're their own libraries in their own respects with their own organizations, and their own, Enzyme and Reactant and Lux become this own pillar of the Julia ecosystem itself. Okay, so that's where I'm going to stop for now because we're over 2 hours. What did I skip? The majority of things. I think I went over everything that was in this chart, but I didn't go over the analysis libraries at all, so nothing to do with global sensitivity analysis, structural identifiability, easy model analysis, none of the uncertainty quantification libraries. I completely skipped everything with jump processes, Catalyst.jl, jump processes, tau leaping methods. I skipped pretty much everything with the PDE solvers, other than a few mentions. I skipped all the SciML architecture, so surrogate libraries, deep equilibrium networks. I didn't even talk about diffie Flux other than some of its internals. I didn't talk about any of the core numerical libraries like the interpolations. I didn't talk about any of the interfaces or parallelism in GPUs. Again, I only covered probably a quarter of the organization, but that was the 2-hour version, so I'm just going to stop right there. If this is something that people like, please like and subscribe, and leave a comment saying that you're interested in hearing about what's going on in data interpolations and surrogates.jl. I'm hoping that if this is a very easy format that maybe they don't have slideshows, I could just sit down and show you what's going on in the docs and the PRs and such, and make this an easy update system, kind of like what we do for the podcast. And if this is a low effort thing to kind of show all the updates, maybe the updates will come out more often. So yeah, if you haven't done it already, again, go to these libraries, like and comment. All these things really help for just being able to show people that being able to show funders that people care, which then improves the libraries themselves. So thank you very much. That was a whole lot to say, and of course there's billions and billions of other things to say about the growth of the organizations over time, and Oh yeah, we also statically compiled a WebAssembly, right? Because if you can static compile to embedded devices and GPUs, you can also go to WebAssembly, so you can try this out, and that's also a project that's ongoing. Again, there's like so many other things to say, but we'll stop it there. And if people are interested, please leave a comment saying, hey, look, I want to hear more about the uncertainty quantification, what's going on there, and we can make other slideshows. That I don't think I'll do it with like the whole nice slide deck and everything, but just some talking points and show you the paper, show you what's going on. I'd be happy to do more. These videos are not so difficult to make as long as I don't have to spend all the time on slideshows. This slideshow I already had because of JuliaCon, so thank you, JuliaCon. But again, we have to keep on doing a new topic every year because this year we have to talk about the nonlinear least squares solvers. We got to talk about the simple DiffyQ libraries and yada yada yada, because every time there needs to be a new set of libraries. So because there's 100 libraries to get through, everyone needs a different JuliaCon. So thank you, everyone.